Robust and scalable in-the-wild 3D reconstruction for realistic and controllable sensor simulation. This supplementary video will review the paper motivation, methodology, additional experimental results, and applications of our approach to simulation, such as mixed reality and texture transfer. Robots, such as self-driving vehicles, learn to handle safety-critical and long-tail scenarios through experience. In addition to learning, we also need to verify that the robot can handle these situations safely. Simulation provides a way to generate a diverse set of experiences efficiently for robot learning and testing. To run the full autonomy system, we require realistic sensor simulation for these scenarios. Existing simulators for self-driving construct scenes by querying from a limited number of CAD assets that are created manually by artists. While these assets are highly controllable and have clean geometries, this creation process is time-consuming and costly. It's therefore not feasible to build assets this way at scale for the wide variety of object shapes and appearances we may encounter in the real world. Additionally, these assets typically do not look realistic, resulting in a larger domain gap. We instead propose to build assets automatically from sensor data captured in the wild by a moving platform. This data is much more cost-efficient to obtain and also captures a wide variety of objects. Specifically, our goal is to take sequences of LiDAR and camera data and automatically generate assets that can be used for simulation. We focus on vehicles, the primary actor in driving scenes. To construct assets from sensor data for simulation, they should have accurate shape and appearance, be easily edited to change appearance, are controllable to change shape based on pose, and should be rendered efficiently. The mesh representation can achieve all of these properties. Meshes specify precise geometry, have modifiable texture and material properties, can be rigged, and can be rendered in real time by many simulation systems. However, current mesh reconstruction approaches struggle on in-the-wild sensor data and do not achieve the desired attributes. This is because the sensor data is sparse and contains incomplete observations of the vehicle. Most previous approaches optimize from a sphere or mean-shaped template mesh to match the sensor data. This initialization lacks prior knowledge of the object to reconstruct, making it difficult to construct a complete and high-quality shape. Additionally, the generated meshes are rigid and cannot be articulated to enable, for example, the wheels of a vehicle turning in a new scenario. These types of changes in shape can provide important cues to the autonomy and should be simulated accurately. Towards this goal, we present CADSim. Unlike existing mesh reconstruction methods, CADSim exploits the fact that CAD models provide accurate priors on shape and geometry, and moreover provide semantic information on how parts can be controlled, such as wheels. We devise a vehicle model representation that takes advantage of this, and use it to initialize the optimization. We then leverage state-of-the-art differentiable rendering techniques to optimize our representation to match the sensor data. CADSim efficiently generates high-quality articulated geometry, as well as realistic modifiable appearance and materials decomposed from lighting, enabling realistic simulation. We now describe in more detail our vehicle parameterization. We decompose the geometry into a vehicle body mesh and wheels. These wheels can be scaled and shifted, and the front wheels can be rotated as well. This is a controllable representation that constrains the degrees of freedom for optimization, allowing for meaningful and realistic shape manipulation. Given our parameterization, CADSim learns the shape representation over a set of vehicle CAD models. This enables us to handle the wide variety of vehicle types that might appear in the real world. Our shape representation only requires annotation of parts for a single vehicle, and we transfer the semantic information to the other models automatically. CADSim can optimize this structured geometry representation, along with the decomposed appearance properties and lighting, to generate a vehicle asset that matches real-world data. Given our vehicle parameterization and good CAD initialization, we regularize our shape to be smooth and have minimal distortion. CADSim adopts a physically based material and lighting model. We encourage our texture to be smooth and for the estimated lighting to be primarily outdoor white light. Our energy model formulation encourages the vehicle mesh shape to match the LiDAR observations. We also leverage a differentiable renderer to ensure the simulated images match the real camera observations. Next, we show novelty synthesis results on the in-the-wild Panda vehicle dataset. Each asset is captured by a moving sensor platform mounted with several calibrated cameras and a LiDAR. We use observations from the left camera for training and observations from the front left camera for evaluation. Our dataset is challenging due to the constrained trajectory, occlusion, and sparse viewpoints. Here's a reconstruction of an SUV, rendered at the test view. CADSim's rendered mess is shown in the bottom right, and the ground truth is shown in the left. Here's another example. We have less blurriness, fewer artifacts, and more complete shape than other approaches. Because of the decomposed material and lighting models, we can also capture specular reflections on the hood and sides of the car. And in the sparse view setting, the neural implicit representation approaches have a harder time rendering at novel views. And compared to other explicit geometry optimization approaches such as SAMP, we have a more accurate shape. We compare our approach against a wide variety of other reconstruction methods. CAD priors enable our approach to achieve higher quality, while also allowing for straightforward editing and controllability. Our approach also has fast reconstruction and rendering times, competitive with other methods. Here we show an ablation result, where we keep our energy model optimization fixed, but change the mesh initialization. Compared to other initializations, our CAD model-based representation better captures details such as the rear view mirrors and better preserves the wheels. CADSim also works on non-vehicle objects, such as motorcycles and traffic cones. We decompose the motorcycles into 3 parts: the handlebar, front wheel, and the body, enabling articulation. We now show CADSim reconstructing static vehicles at scale. We first show the original sensor data, LiDAR on top, camera on the bottom. We then show the reconstructed CADSim geometries overlaid in the scene, rendered by their normal map. CADSim geometries match the original vehicles well, enabling high-fidelity virtual world creation at scale. We can then place CADSim-generated assets in the same locations that they were recorded in, and render the sensor observations to demonstrate that they match well with the original sensor data. Top is the real LiDAR and camera image, while the bottom is the simulated LiDAR and camera data with CADSim meshes inserted into the scene. Our results are consistent across sensors and viewpoints. Here we show simulated results on the front left and front right cameras. Our rendered meshes match well with the real foreground pixels. We now show insertion of CADSim assets into new scenes. We can render the CADSim asset at a new pose and blend the rendered image segment into the new scene. We can manipulate in 3D the position and rotation of the added car. Because our assets are multi-sensor consistent, we can generate the LiDAR point cloud and the camera image for the modified scene. Notice the wheels are spinning when moving forward and backward, and the wheels are rotating to model turning. We can also generate interesting new scenarios with CADSim assets. Here's the original real scenario. We can insert a CADSim asset aggressively turning right into our lane. The simulated camera and LiDAR data are blended seamlessly into the original scenario, creating a more interesting long-tail scenario. Here's another example. We show the original scenario first. We then insert a moving vehicle performing an aggressive lane change. The complete shape reconstruction allows for rendering of unobserved parts of the car. And we can generate these interesting mixed reality scenarios at scale. Finally, CADSim naturally supports texture transfer and synthesis. We first show the real image sequence. We can now replace the texture of 2 of the cars with the texture of the first car, creating a new scenario for autonomy to experience. This technique can be used to generate diverse textured assets not seen before to enlarge our asset library for camera simulation. Thank you for watching.